Okay, let's look at two optimization problems. Just good practice problems that relate to just the kinds of problems that you typically see with optimization. I want you to be used to seeing these. Okay, so this is one that's really similar to one on the assignment that you did on the first Math Excel assignment, right? Now I'm going to put up another one today. It's just like probably two. I'll probably put like 2 problems up per assignment, and we'll end up doing like 4 assignments on this stuff, just so you get through a variety of different kinds of optimization problems. So this is pretty similar. Farmer plans to fence a rectangular pasture adjacent to a river. You can see the beautiful picture there. The pasture, this is a little different though. This time, instead of the constraint being on the amount of fencing, the constraint is on the area of the pasture. So say this is based on, you have to have a certain area available per cow or something, right? So we know what we have to have available, and we're going to configure the pasture to fit that constraint, area constraint. So it's got to contain 245,000 square meters in order to provide enough grass for the herd. What dimensions will require the least amount of fencing if no fencing is needed along the river? So it's really similar, isn't it, to the one we just did. So we've got a nice picture. So we've defined the variables in terms of the picture. So now we just need to come up with our primary equation. So what's the primary equation here?
2y plus x.
Okay, but what we got to know, we always have to define what is the quantity that we're talking about here.
Right.
So we'll call it perimeter. So P equals, based on our picture, we got 2y plus x. Okay. What's wrong with that?
2 variables.
2 variables. Okay, so we need a secondary equation. Or an equation of constraint. So, where's that coming from up here? Somebody hasn't contributed yet. Where's that coming from? Equation of constraint. Area. Good. Good. So area is going to be, in terms of x and y, is what? X times y. Good. So x times y equals 245,000. So, I mean, it's not a huge consideration here, but probably which one do we want to substitute for? Pretty even in this case, but slight edge to x because it just shows up in, there's a 1x there and 1x there, right? Probably just a little bit easier. So if I solve for x, I just get 245,000 over y, so we put a box around it, and there's our substitution equation, right? And so then we end up with, if we do that, we're going to get P equals x, which is now written in terms of y. So we can write this as P of y. So the only other thing we need to do before we just launch into, table talk here is we got to come up with the domain, right? So that usually takes a little bit of thought because it's not just mathematical. We've actually got a real thing going on here. So what's our domain? We've got to think about what's the smallest that y could be. It really can't equal 0 because x is defined in terms of y on the bottom, right? I mean, if y approaches 0, then x is going to get really big, isn't it? Right? Okay. And 0, it's not that big of a deal because we know it's not going to make sense anyway. It's not going to give us any, that's going to be a really bad way to try to fence this pasture would be to have the fence right along the river, obviously. I mean, it just doesn't make sense as a choice anyway. So our lower limit is going to be 0. Now, what's our upper limit? And always think about this. You want to think about this in terms of the competing variable because there's always going to be this inverse relationship, right? X and y, as x gets big, y gets small and vice versa because we have a constraint on area, right? So we'll look up here to our area equation, and probably the best place to look is right here, right? We know that when x gets big, or when y gets big, x gets small. Well, how's that going to work? X is gonna get small as y approaches what? Well, no. I mean, y theoretically could approach infinity here, right? It's gonna be a really dumb way to do it. It's gonna take a lot of fencing. But if we have to enclose some finite amount of area, right? I could squeeze this thing down so as the width approaches 0, the height is gonna have to approach infinity to enclose that area. Horrible idea, right? But there really is no upper limit there's no firm upper limit on what the amount of fencing is gonna be. Clearly, we're gonna get some much better answer between 0 and infinity, right? Okay, does that make sense? Think about this. This is non-physical, because physics doesn't work this way, but if matter were infinitely partitionable, so I could cut it into infinitely small pieces. A drop of water, if I squeezed it down infinitely far, would spread out infinitely far, right? I mean, it doesn't really work that way because we actually have finite little particles in there that are prohibit that from happening. But that would happen. Mathematically, that's what would happen if I took a drop of water and squeezed it down so flat that it approached 0 thickness. It would spread out infinitely far, okay? So now we got to here, right? We figured out our domain. There's really, y could be any positive number. We just got to find the one that works. We've got our perimeter function as a function of a single variable. So now all we have to do is just take the first derivative, and if we decide it's convenient, we'll take the second derivative. If not, we won't do it, right? But we're going to have to just make a table and then find our maximum on this domain, okay? So first derivative. Derivative of 2y with respect to y is what? 2. So we know we're going to get a 2. Now what about this term? How do we deal with the y on the bottom? Billy, how do we deal with the y on the bottom? -1, okay? So 245,000 y to the -1. If I differentiate that, I'm going to get minus, 245,000 y to the -1. The derivative of would be to the -2, but I'm going to bring the -1 down front with this. You're right, so 245,000 y to the -2, exactly. So then that's going to put the y squared on the bottom, right? Okay, now while we're at it, it's pretty easy to take a second derivative, isn't it? Right, so we might as well take one, I think. I mean, you might decide differently on this. Derivative of 2 is nothing. Here I've got a negative 245,000 y to the -2, right? We can even write it that way if we want to. So what's the derivative of that?
490,000.
That's a negative. So it's going to be positive 490,000, but we really don't even care about what it is, honestly, because we're not going to solve for anything there. We just want to know what the sign is. We'd probably figure out what the number is. Divided by y cubed. But we could even just think about that as some number, some positive number divided by y cubed, and that's good enough. Because for any positive value of y, what's that tell us about the sign of the second derivative? Positive. Yeah, it's positive, right? So if it's always concave up, then any critical number we get for the first derivative is going to have to be the minimum, which is what we're looking for, right? Okay, so now here's all our here's the 3 derivatives. Now, if we want to do some work with one of these, and this is what I was talking to you about, Gabe, so now we could take let's take this first derivative here. It's supposed to be a 2 there. Let's take our first derivative, and let's find a critical number. Now we can just set all that equal to 0 and solve, right? So 2 minus 245,000 over y squared equals 0. If I want to solve that, I could just add that to the other side. We just like cross multiply, divide by 2. So y squared would equal what's half of that? What is that, 1, 2, 2, 5? Is that right? So if I square root that, I'm gonna get y equals plus or minus the square root of that. Who knows what that is? Is that some nice number, somebody? It's like that. Mike?
350.
What is it?
350.
350. Okay, do both of those critical numbers make sense? Just positive one, right? So now if we made our table, it's a pretty simple table. We just got y, p, p prime, p double prime. Domains everywhere. The one critical number we get is at 350, which is a 0 of the first derivative. And we already said the second derivative is positive. So we know that that's going to be a horizontal tangent, upward concavity. It's a relative minimum, right? So we found it. We found the value of y that's going to give us our minimum. The original question wants to know what dimensions. So dimensions. So y is going to be 350. To find x, we'll just plug it in there, right? So x equals 245,000 divided by 350, which is so 50. It's going to be something that starts with 5, isn't it? What is it? 500? Is that what it was? Is that what you said? What we said? 700. Oh, 700. There you go. 300 by 700. Okay? Yes.
Is it a coincidence that x is equal to y?
Nope. Not a coincidence. It's always going to be that way. That's, no matter what. For this situation, if you only, we don't need to use, one side's provided for us, one part of the perimeter is provided for us in this situation, it's always going to be that ratio.
You're looking for large area.
Looking for the minimum fencing for a fixed area. Yeah, that'd be the shape that would most economically use the fencing. That's what the math gods tell us, so we'll believe it. Okay?
So in the future, we would be using that.
Yeah. Oh, you could absolutely. Yeah.
X equals to y, but
Yep.
what I'm saying is you don't know. Well, you don't know the root, so it's not, you're still going to solve.
Yeah, you would have solved for the dimensions, wouldn't you?
Yeah, because you don't
Yeah.
know the root.
Yeah. Yeah, you're right. Yeah. No. You could do that without calculus though too, because if you knew, you could set up a system of 2 equations and solve it that way if you want. With calculus is pretty easy. Probably just about as easy to do with calculus. Okay, this doesn't seem like a very cool question, but I always like to go through this one for my classes. This is pretty cool. It gives us some pretty profound insight into the way things are in the world. So 4 feet of wire is to be used to form a square and a circle. Okay, so in other words, we're going to start with 4 feet of wire. So from there down to there is 4 feet. Somewhere along that wire, we're going to make a cut, and we're going to bend one of those pieces into a square and one into a circle. Okay? How much should be used for the circle to enclose the maximum total area? See what we're getting at? So if we make the cut, let's say we make the cut like right here. Okay, and then this piece from there to there, that's going to be bent into, let's just say, a square. Right? So we're going to turn that into a square. And this piece from there to there, we're going to turn into a circle. And we want the areas of the 2 shapes to be maximized. Okay? So what do you think? How do you set this one up? This is a really cool question. could be the area of the square plus the area of the circle, for sure. Okay, but in order to do that, we still have to define, the variables here.
One could be four, one could be X, one could be four.
Okay, good, so what are you saying X is then?
The area, it's the circle.
Okay, and before we even get to the circles and the squares, what is X in terms of our piece of wire? The length of one piece, right? So we could say something like, let's just say that this distance right here, if the whole thing is 4, let's call the yellow piece of wire X. The length of the yellow piece is X. Okay? Doesn't matter which one we attach to the square and which one we attach to the circle. It really makes no difference. So then if that's the case, Kirk had it right then. The other piece is going to be the entire length minus X. So that's 4 minus X, right? And so we had to be able to come up then, if those are the perimeters, we had to be able to come up with the areas in terms of those perimeters, right? Okay, so we know that if we're going to let the side length of the square, let's just call that S. So X is really the perimeter of the square, isn't it then? Everybody agree? So S would just equal X over 4. Okay? Everybody good with that? Yep. Okay. And so the area of the square is just going to equal side length squared, right? X over 4 squared. Okay, what about the circle? This one's a little bit tougher. This is the circumference of the circle, right? So we got circumference, so 2 pi r equals 4 minus x. We need the radius to come up with the area, don't we, right? So the radius then is going to equal 4 minus x over 2 pi, unfortunately, right? And so our area for the circle, just pi r squared. So we're going to get pi times the quantity, 4 minus x over 2 pi squared. Okay, so that's kind of inconvenient. So the area here is going to be, we could rewrite that as 4 minus x squared, we square the top, over 4 pi squared on the bottom, but we'll cancel one of those pi's, so we just get a 4 pi on the bottom. Everybody good with that? I'll just pause there for a second. Okay, and Ryan, you were right. We wanted to combine, our primary equation's got to be the quantity we're trying to maximize, which is the combined area. So the area of the square plus the area of the circle should be our combined areas. Okay? So the primary equation looks like A, only one variable, x. A of x equals x over 4 squared. Well, let's just make that x squared over 16, how about, right? Plus this one. Well, while we're at it, why don't we go ahead and, maybe we ought to square out the top of that, right? Might as well make it a polynomial. Okay, so that's going to give us x squared minus 8x plus 16 over 4 pi. Oh, how come there's only 1 pi on the bottom? Is that the question?
No, I was just wondering because I thought that you squared it. What happened to the pi up front?
So I ended up on the bottom, when I square all this out, I'd get a 4 pi
yeah,
squared.
never mind.
So one of those cancels. Okay, so there's our total area. Now let's look at the domain of this. And we can just look at this in terms of the piece of wire. What's the smallest x could be? 0. Yeah. 0 would mean, that's equivalent to saying we're going to use all the wire for the circle, right? The biggest it could be, and I guess we could actually have it be 0, couldn't we, right? The biggest it could be would be 4, so we're using it all for the square, or somewhere in between, right? So now we just have to do that calculus. That's a little harder looking calculus to do, but we can do it. So we'll just differentiate term by term. First part's pretty easy. What's that? Derivative of x squared over 16. 1/8 x. So we'll just leave it as x over 8, how about? Plus. Now for this part, why don't we just pull the 1 over 4 pi out front? and then just differentiate that polynomial. So what do we get?
2x minus
Okay? Do we want to do a second derivative? I'd say, yeah, it's pretty easy to do, right? So our second derivative, derivative of x over 8, 1/8. Derivative of 2x minus 8. So on our domain, what can you tell me about, actually, what can you tell me about the second derivative everywhere?
8.
It's positive, right? It's constant and it's positive. Positive is the important thing, right? It's always going to be concave up, okay? What's that telling you right away? There's only, so there's, if the concavity is always up, right away, just, it might give you a little hint. So we'll come back at the end and I'll ask you to kind of revisit where, you know, what, if you kind of, hindsight's always 20/20, when we're all done with this problem, I'll have you go back and reconsider the ramifications of just what that second derivative is. And after having done it, I bet you'll be able to say, oh, okay, I can see how I probably could have seen that right from the beginning, what the outcome had to be from this one. And that's, and once you get better at math, you kind of, those are the kind of things you'll kind of start to see, you know, is that a lot of times you can just avoid having to do any calculus at all. You can make a pretty elegant argument that just circumvents all of the math completely on a problem like this. And that's the way to go. That's the way to go. There's some guys I went to college with who, oh my God, these guys were so smart. It was ridiculous. We do these problem sets. I had a quantum mechanics problem set that was over 100 pages long, 4 problems. These things were just, these guys would come in, could have killed them. They'd come in with this little 4 or 5 page problem sets, you know, and here I got a book. I mean, you literally had to get the big industrial stapler just to staple the thing. And they'd always use these super elegant arguments, like they'd appeal to the isotropy of space to avoid all this math. It's just, God, how did you come up? But they were great proofs because they were so simple. They just, you know, they were able to just sidestep all the math and come up with some really cool argument that just prevented you from having to do it. It proved it much more easily. So when you can, you always want to look for those things. They're nice. Let's go back to our first derivative row here and let's find the critical numbers, right? If we set this thing equal to 0, when does that equal 0? So that's going to equal 0 when, let's just write it out, I guess, right? So x over 8, if we redistribute here, what are we going to get? X over 2 pi minus 2 over pi equals 0, so I can do that. Okay, we good? Factor an x out of the left side, so I get x times 1/8 plus 1 over 2 pi equals 2 over pi. Good? Okay, so let's go ahead and how about, we need a little more space here, so just follow along there. Let's just do this on the next page, just got a little more room. So let's simplify this big fraction. What if we get a common denominator? So I could multiply this one by 4 over 4. Actually, I could multiply this one by, 4 over 4 and this one by pi over pi. So I get pi plus 4 over 8 pi. Is that right? Did I do that right? I think so. Okay. Equals 2 over pi. So we'll multiply each side by the reciprocal. So I get 2 over pi times 8 pi over pi plus 4, right? I want to solve for x. So those guys cancel, and I end up with 16 over pi plus 4. That's my one critical number. So what is that roughly? just as a decimal. So that's like 16 over a little more than 7, so it's like 2 point something. Right? Okay, so for our table, if we go back now, is there even room for a table there? Now let's go to the next, do it over here. So for our table, got X, got A, got A double prime. What did we say? We went from 0 to 4 in our domain. The one critical number we got was 2 point something. Okay, but that was a 0 of the first derivative. But what did we say the sign of the second derivative was everywhere? If we go back and look,
Positive.
positive, right? It's always positive. So now are you seeing, that's significant, isn't it? If we've got a horizontal tangent and concave up, our one critical number has to be a minimum, right? Do you agree with that? In fact, we never, to say, what if we'd had multiple critical numbers? Well, we probably couldn't have, but even if we did, we could never have had a maximum, could we? Because the concavity was always concave up on the entire domain, right? So what's that tell you? Where does the extreme value have to occur? If the function's concave up everywhere on the interior, it's got to be at 0 or 4, doesn't it? It's got to be at an endpoint, right? When we make our table, we know that that's going to be a minimum. So the only places where we could have maxima would be there or there. Because this problem really becomes an absolute extremum problem, doesn't it? We've got a closed interval and we're trying to maximize a value on a closed interval. We want to find the maximum of a function on a closed interval. So if we go back and evaluate our original function at 0 and 4, let's see what we get. Okay, at 0, this term goes away completely, right? So let me just grab a picture of that. Right, so we get so you end up with A of 0 equals 16 over 4 pi, right? Everything else goes away. 16 over 4 pi is just 4 over pi. Okay, what about A of 4? If I take A of 4, I'll bet you money this is going to go to 0. It has to, doesn't it? Where did that term come from? Right, this was the area of the square, wasn't it? And this was the area of the circle. Well, if we're using the whole wire for the square, then the area of the circle is going to be 0. Just like before, we used the whole length of the wire for the circle, so that went to 0, which it did, right? We can check it, but we're going to get 16 minus 32 plus 16. What do you know? We get 0. And so when A is 4, we get the area is 1. Okay? What's bigger? 4 over pi is bigger than 1. So what's the moral of the story? We use it all for the circle, don't we? Right? Okay. That tells us something pretty profound. Now, we could have used any shape other than a circle, and which shape would have won? The circle would have won, right? So that gives us a little insight into the way things are. That tells us, in fact, we could do, if we wanted to go like one step further, this would be really cool. How much time we got?
15 minutes.
15 minutes, that's enough time. So if we were to take, let's just take regular polygons, right? If we take regular polygons, the area of a regular polygon as a function of side length and number of sides is s squared n over 4 times the tangent of pi over n. Okay, where S is the side length, n is the number of sides. So if we combine that with the fact that to make this a fair fight, we're going to make the perimeters all the same, right? So if we have an n-sided polygon, what's the perimeter of an n-sided polygon? The side length S.
S plus the times
S times n, yeah, right? Side length times number of sides would be perimeter. Okay, so we could say perimeter equals S times n, so side length is really just equal to perimeter divided by number of sides. But the perimeter is going to stay fixed, right? So the perimeter, to keep all of them the same, all we're going to change is we'll keep the perimeter the same, but we'll change the number of sides that we're using to make that perimeter and combine and compare the areas, right? So if we make that substitution, then we get A as a function of n equals every place we have an S, we can replace that with a P over n. So we got an S squared. So let's just multiply that part by S squared, how about? Right, so we've got n over 4 tangent of pi over n times S, which is P over n squared, right? So we come up with the formula A of n equals P squared. I'm going to have a P squared over an n squared, so I can cancel one of those. On the bottom, I'm going to get a 4n tangent of pi over n. Now, that might not look like much, but let's cheat and use Desmos. Let's look at the graph of that. Let me see something cool here. All right, so, man, you didn't used to be able to do, there are so many cool tools out now for doing math.
You wish you had these tools in college?
I really do. Would have made it so much more fun. Okay, so let's put that in. So A equals, I'll show you a cool trick on Desmos here too. So equals P squared divided by, I wonder if I need to do A of, oh, I guess I don't. Oh, I'm going to call it y too. I need to call it y. So A is going to be y and n is going to be x. I think in Desmos. We have to do that. P squared divided by 4x. We'll add a little. I'm going to be able to pick values for P. We can let the perimeter be whatever we want. Let's just make it 10. How about? On the bottom, I've got 4x tangent of pi divided by x. Okay? Oh, this is going to be cool. It's going to be really cool. And let's do, if I go click here, I can make that a table. Yeah, okay, this is super cool. I remember how to do this now. Okay, so we go. Okay, and we'll go up here, and let's just delete these rows, because they don't, side lengths of negative numbers don't make any sense. Can't have 0 side length. I can't have 1 side length. And what's the area of a 2-sided polygon? 0, okay? Okay? So now let's set up, so this looks nice. We'll go from 2 out to 12 by 1s on the x-axis, and for y's we'll just go from -1 up to, I don't know, say 8 by 1s. We don't need those minor grid lines. That's pretty cool. What do you see there? So we get, of course we get, let's get rid of that even, how about? So x is the number of sides and y is the area. What do you notice?
The more sides, the greater the area.
Yeah, the more sides, the greater the area. And that's it's going to slow down the rate at which you're increasing area, but it never stops, right? Okay, so that tells us something pretty profound then, right? So if we let the number of sides approach infinity, we could do a limit. If we have more time, we could like look into this. There's a limit, there's part of the limit there that would be a little tough for us to do, but we could get through it if we had time. The tangent part. So we'd write it in terms of sines and cosines, and we could do it. But what we'd find is we'd approach some finite value, which would be, what do you think it's going to be? The area of a circle. Yeah. Okay, so that's our proof. A pretty informal but pretty powerful proof that a circle is the most efficient way of enclosing area, right? Okay, so you could extrapolate that, add another dimension to this instead of two-dimensional situation. What if we made it a three-dimensional like we live in? The circle generalizes to a sphere. And what we find is that any kind of polygonals or a polyhedral shape, you're going to find that the sphere is going to be the most efficient way of enclosing the area, right? Okay, now let's think in nature about where that would be important. Where would you want to have a really efficient enclosure of volume? Where would you want the ratio of your volume to surface area to be really high, where you have low surface area and high volume? Where would that be an issue, do you think, for creatures? Let's look at, like, in an evolutionary sense, creatures that have had to adapt to environments where that would be important. Where would that be important? Eggs? Maybe. But let's say even adult creatures, where would it be, in what kinds of environmental conditions? Let's take a look at warm-blooded animals. Where would you be, like, can you think of a place where it would be really critical to minimize your surface area?
Or in the desert.
Where it's really cold. Yeah, where it's really cold, right? Because the danger there would be that you want to, the more heat you lose, you couldn't maintain a constant body heat if you were a warm-blooded animal, if you were losing heat too fast, right? So then, by our hypothesis here, if we were going to say we were new to Earth, we were aliens, we would say, okay, we probably would surmise then in areas where there are really cold waters, where you're going to have a, water's particularly bad because it's a good thermal conductor, right? So we'd probably find that animals would be pretty spherical looking, animals that lived in really cold waters, right? And they'd probably be pretty big because the larger the volume, that you're actually going to, this isn't just uniform for all volumes. What you're going to find is, if I drag my little, watch this, if I drag my little scale along here, it changes, doesn't it? Right? So what you're going to find is that for bigger volumes, that efficiency is going to be even better, right? So we'd probably also surmise that we're going to see lots of bigger creatures, big bulbous creatures where the water's really cold. Well, do we? Seals, whales, narwhals, whatever, right? They're all, you get the idea, right? You're going to tend to get really big animals that have pretty spherical shapes, right? Okay, now let's go to the other extreme. So the other extreme would be like if you were going to look maybe in really, really hot climates, animals have to be able to cool themselves, right? So you would want the opposite. You'd want animals to be able to get rid of their heat easily. So you should see animals that are especially non-bulbous, right? That really accentuate, they have lots of points that get as unspherical as possible, right? What do you see? If you look at the desert, you see lots of really bulbous creatures. Now you might say, okay, I got you, what about elephants? But elephants are massive cheaters because they've got these radiators called ears, right? And so that ear is totally throwing things out of whack. It creates all this extra surface area, right? And what is the shape of an ear? It's really thin, it's planar, so they're totally cheating at those, right? But if you throw elephants out of there with their big ears, you got giraffes, the animals are very much different, right? They're going to be rangier and longer, and they're going to have they're going to try to maximize their surface area, right? And animals would tend to be smaller, right? In hotter climates like that, you're going to tend to find really small mammals too.
What about a rhino?
What's that?
Rhino.
Rhino, what about a rhino? Oh, they're in the water all the time.
Are they?
Yeah,
Oh,
right?
I thought that was a hippo.
Hippos too.
Oh, they're both? Oh.
But you're gonna probably find
Out of the water.
some anomalies there, but in general, that's gonna be the case. That's gonna be the case. You can look at humans too. Humans that live, in really hot regions have tended to be tall and, angular.
The reals.
Yeah. And then Neanderthals, who were living in the most extreme regions, You know, they were much more compact.
That works the same for the opposite way, though, right? Like, if you're trying to get nutrients in, you want this small.
Right, if you wanna get
Like- like a
right,
cell.
right, exactly. If you wanna get nutrients in, like for a cell, you'd wanna go the other way, correct. And I don't know enough about cellular biology to know what the mitigating factors would be. Do you wanna be able, is your cell wall vulnerable? Do you wanna be, I don't know, if you're playing like a game of cellular risk, I'm not sure what you would try to do there. Would you try to really get your, how much stock do you put in trying to minimize the surface area of your cell wall for defensive purposes, as opposed to, I don't know nearly enough about that to even talk about it. But that's interesting, so that's kind of the direction, if you're interested in biology, by the way, this is the direction that biology is now going. I mean, the frontiers of biology are gonna be done by mathematicians, physicists, people that do molecular, that do like biophysics. This is where, I mean, really, that's where it's gonna be in the future. Everything's gonna tend to be much more tightly focused, and it's gonna be much more built on models, and I know that for a fact. I mean, you're gonna do math regardless of what you go into. But, I mean, if you're going to the sciences. Obviously, much more so with physics, than you would with other stuff, but that opens up lots of niches for you, and the other sciences as well, the life sciences as well. So. Whew.
Wow.
Kind of cool stuff though, huh?